Graphical methods provide a visual impression of the data and can often reveal features that summary numerical descriptive values cannot. On the other hand, descriptive summaries provide information that graphical displays cannot. So we use numerical descriptions together with graphical displays to describe data. To begin with, measures of center estimate a list's typical value, and measures of spread estimate the amount of variability, i.e. lack of consistency in the data. There are typically several reasonable choices for which numerical description to use to investigate a question of interest. For example, one could use the median or the mean to describe a typical value in a list. The decision about which measure to use depends on the properties of the measures. Chapter 2, the concepts we'll be covering: mean and median, measuring spread, quartiles, 5-number summary and box plots, spotting suspected outliers, measuring spread using standard deviation, and choosing between measures of center and spread. The most common measure of center is the arithmetic average, or mean. To find the mean, we pronounce this x bar, of a set of observations. You simply add the values and divide by the number of observations. So x bar equals the sum of the observations divided by the number of numbers, n. Or in more compact notation, we write this as x bar equals sigma x divided by n. The sigma is the Greek letter, capital Greek letter sigma, which stands for sum. It just simply means add a bunch of things. Here's an example. The salaries at a small company are $25,000, $26,000, $31,000, $45,000, and $170,000 per year. The mean salary is $59,400. If we don't include the salary of $170,000, the mean salary is $31,750. Notice that the mean changed dramatically by just removing one observation. We say that the mean is not a resistant measure of center because it cannot resist the influences of extreme observations. The median is another common measure of center. The median is simply the middle of a distribution, the number such that half of the observations are below it and the other half are bigger above it. To find the median of a distribution, you arrange all observations from smallest to largest. If the number of observations is odd, the median is the center observation in the ordered list. If the number of observations is even, the median is the average of the two center observations. For example, suppose we have the commuting times in minutes of 20 randomly selected New York workers, and we'll calculate the mean and median. The mean, just simply add up the values and divide by the number of numbers. In this case, the mean is 31¼ minutes. The median. We arrange the observations in order first, in this case from low to high. Locate the middle number. Since 20, n, is an even number, the median is between the two center observations. So we just average them. So the median in this case is 22½ minutes. The mean and median measure center in different ways. Both are useful. So how do they compare? Well, the mean and median of a roughly symmetric distribution are very close together. If the distribution is exactly symmetric, the mean and median are exactly the same. In a skewed distribution, the mean is usually farther out in the long tail than is the median. So for example, here's a roughly symmetric distribution. The mean and median are about the same. For a skewed distribution, the median is around here. The mean is a little bit further toward the tail. It gets pulled by the more extreme values. Now for measuring the spread, suppose we have 4 factories producing cream soda in 20-ounce bottles. We take samples from each of the 4 factories. These are listed in the table below. Which of the 4 factories is doing the best job at producing 20-ounce bottles of cream soda? Well, if we look at the mean, we can see that factories C and D are producing below what they should. But factories A and B are producing on average exactly what they should. Is there any difference? Well, on average, they put the correct amount of soda in their bottles. However, factory A is less consistent than factory B because its values vary more widely. So a measure of center alone can be misleading. A useful numerical description of a distribution requires both a measure of center and a measure of spread. We'll start by talking about quartiles. To calculate the quartiles, we arrange the observation in increasing order and locate the median. The first quartile is the median of the lower half of the observations. So those are the lower half to the left of the median. The third quartile is the median of the upper half of the information. The interquartile range is defined as the third quartile minus the first quartile. The minimum and maximum values alone don't tell us a whole lot about the distribution. Likewise, the median and the quartiles don't tell us a lot about the tails of a distribution. So to get a quick summary of both center and spread, we combine all five. The five-number summary of a distribution consists of the smallest observation, the first quartile, the median, the third quartile, the maximum observation, written in order from smallest to largest. So, for the commuting times of the 20 randomly selected New York workers, we found the median at 22.5. The first quartile, we look at the lower half of the information and find its median. So that, again, is in the middle between the two values, so we just average them. So the first quartile is 15. The third quartile, once again, we find the median of the upper half of the information. And in this case, that's the average of 40 and 45. And then we get the minimum value and the maximum value, and that gives us the five-number summary. The five-number summary divides the distribution roughly into quarters. And this gives us a new way to display quantitative data, called the box plot. So to make a box plot, we draw and label a number line that includes the range of the values of our distribution. It's the variable. We draw a central box from the first quartile to the third quartile and indicate the median inside the box, and then extend the lines, also called whiskers, from the box out to the maximum and minimum values. In addition to serving as a measure of spread, the interquartile range, the IQR, is used as a part of a rule for identifying outliers. We'll call an observation an outlier if it falls more than 1.5 times the IQR above the third quartile or below the first quartile, so within a range. In the New York travel time data, we found the first quartile was 15, the third quartile was 42.5, so the interquartile range, the difference between those two, is 27.5 minutes. For these data, 1.5 times the RQR, 1.5 times 27.5, is 41.25. So we take that number, 41.25, subtract it from the first quartile, and we get minus 26.25. We take the third quartile and add that number to the third quartile. So 42.5 plus 1.5 times the IQR, 41.25, and we get 83.75. So any travel time shorter than minus 26 minutes or longer than 83.75 minutes, we consider to be an outlier. For the data for the travel times, 85 falls outside of that range. So we identify 85 as an outlier. So now we're going to construct a box plot for the New York travel times. We find the median, the quartiles, the five-number summary. And we've determined that even though the maximum value here, 85, we determined was an outlier, we're not going to throw it away, but we're going to create the box plot without that value. So we first draw a box around the first quartile and the third quartile and then locate the median inside the box. And then we tack on the minimum value using a line and the new maximum value excluding the outlier, and then we indicate the outlier. So let's put this information to use. Suppose we have the 5-number summaries and box plots for travel times to work for 2 different states, New York and North Carolina. So we have these back to back. In comparing the two, we can see that the medians are roughly the same, the minimum and the maximum values are roughly the same. The real distinction is that the values for New York are generally more spread out. That middle box is much more spread out. Now we'll talk about another measure of spread. The standard deviation measures the average distance of the observations from their mean. It is calculated by finding an average of the squared distances and then taking the square root. The variance, we take the difference between all of the values in the mean, square them, add them up, and divide by n minus 1. Standard deviation is the square root of that. So here's an example. Suppose we have data on the number of pets owned by a group of 9 children. We first calculate the mean, and then calculate each deviation, the observation minus the mean, and we'll do some stuff in a minute. So the average is 5, x bar is 5. Here's one deviation, so between the value 1 and the mean is negative 4 units. The deviation from the number 8, so 8 minus 5 is 3. Now, as is it with the table here, we list all of the values of the variable. So 1 through, we have all of these values here. We subtract the mean from each of them, and then we square each value. Square each deviation, and then we find the average squared deviation. So we calculate the sum of the squared deviations, and we divide by n minus 1. This is called the variance. And then we take the square root of the variance, and that is called the standard deviation. So the average squared deviation, in this case, the sum of the values is 52, and we divide by 9 minus 1, or 8, and that average is 6.5. That's the variance. The square root of that, the standard deviation, is about 2.55. We now have a choice between 2 descriptions for center and spread. We have the mean and the standard deviation, and the mean and the interquartile range. How do we choose between those? Well, the median and the IQR are usually better than the mean and standard deviation when describing a skewed distribution or a distribution with outliers. You use the mean and the standard deviation only for reasonably symmetric distributions that don't have outliers. Note, numerical summaries do not fully describe the shape of a distribution. It's really important to always plot. Now we'll talk about, in general, how we'd organize a statistical problem. So I'll be asking you to do some more complex problems. There's a 4-step process here that can be applied to many of the statistical type problems, and I'll do an example of that in a minute. So we begin by stating, what's the practical question in the context of the real world setting? So what do you want to know about? And we state that as precisely as we can. And then plan, what specific statistical operations does this problem call for? We've already had several with means and medians and standard deviations and whatnot. The next thing is to do. So we make graphs and carry out the calculations needed for the problem. And then conclude. Give your practical conclusion in the setting of the original problem. So let's do an example comparing tropical flowers. 2 researchers from Amherst College studied the relationship between varieties of tropical flowers on the island of Dominica and the different species of hummingbirds that fertilize the flowers. The researchers believed that over time, the lengths of the flowers and the forms of the hummingbird beaks have evolved to match each other. If true, then flower varieties should be fertilized by different hummingbird species should have distinct distributions of length. So we will compare the distributions of lengths of 3 varieties using graphs and numerical descriptions. So we start by stating, do the 3 varieties have distinct distributions of length? How do the mean lengths compare? We start by planning. We'll use graphs and numerical descriptions to describe and compare these 3 distributions of flower lengths. Now, on to the solution to the problem. So we collect data on 3 varieties of tropical flowers. These are given in the table below. Distributions of these data will be shown using stem plots. The mean and the standard deviation are also given here. Notice we can actually compare at this time and say, well, the Baha'i variety seems to have a much higher mean length than the other 2. But it would be simplistic at this point to draw a conclusion just by comparing the numbers. There's more to it. So let's look at the stem plots of the 3 varieties. The Baha'i variety, the red variety, and the yellow variety. In this case, it becomes a little more clear that the Baha'i variety, in general, is longer than the other 2, and there is some overlap with the red and the yellow varieties. The Baha'i and the red varieties have somewhat skewed distributions. So next time, if we were to do this, we might consider using the 5-number summaries and box plots instead of stem plots, means, and standard deviations. However, we'll conclude, based on this information, the 3 varieties differ so much in length that there is little overlap among them, except maybe in the red and the yellow. But in particular, the Baha'i variety flowers are longer than either of the other 2, and there is no overlap there. So review what we set out to do here. We calculate, interpret mean and median. We compared the mean and the median. We calculated and interpreted quartiles. Construct and interpret the 5-number summary and box plots. Determine suspected outliers. Calculate and interpret standard deviation. Choose appropriate measures of center and spread. And then organize and carry out a statistical problem.